Okay, thank you for the invitation. Thank you for the introduction. I think it's my first time in Mexico, and it seems really nice here. So I'll discuss about the GIT construction and the connection to moduli. So there are some references. First of all, there are my surveys. I mean, I would say guide to literature, so there are two of them. One is GIT and moduli with a twist. And the second one is perspectives on moduli. Both of them are published, but of course they are easily available from archive. And there are two standard GIT references. First of all this is the absolute standard, the Mumford et al., the GIT, Geometric Invariant Theory. And then a book that I like a lot is Mukai, maybe Introduction to Invariants and Moduli or something. There are, of course, many others, but I think for the purpose of what we are doing here, it's enough. Okay, so there are 5 lectures, and let me just briefly give a plan. So today we'll just do an intro to GIT. Tomorrow I'll discuss about linearizations and variation of GIT. The third day is tools. I'll mostly discuss about the numerical criterion, Luna slice theorem, and then I'll also discuss maybe by the Kempf-Ness approach, Kempf approach. The fourth day would be examples. Of course, kind of the examples will be throughout the talk and throughout the lectures, but here we'll discuss in more detail. So first of all would be about the curves, hypersurfaces, and K-freeze, low degree. And the fifth lecture, this is further topics. And among that, maybe I'll discuss about GIT and Hassett-Kiel. And then maybe comparison, GIT versus other approaches. And finally, maybe about the case stability. Okay, so this is, I don't know, maybe more than a plan. This is more like a wish list, so we'll see. We'll see how far along we'll get here, and I don't know. But I mean, kind of the main idea is to give you an idea, and of course we'll prove very, very little, as Eduardo says. So basically, we'll focus on giving a big picture, and today I'll just try. Okay, and just to connect, let me connect to previous lecture. I mean, kind of the big goal is to construct and compactify moduli spaces. In particular, I mean, this lecture series, all of them are concerned mostly with MG. This is the moduli space of genus G curves. And the point is that even if you care about the smooth curve, so this would be kind of like the smooth curves, even if you care about the smooth ones, in order to say something meaningful about the moduli space, you always need to compactify, you need a compact space, you need to allow singularities. That's kind of, so the goal of these lectures, I mean kind of all the lectures here more or less, is to describe this moduli space and say something about it. So there are several approaches to constructing, so there are three main approaches, I would say, to construction of moduli. And let me just give the big picture. So the first one, and maybe the most natural, I would argue, is GIT. And this is based on varying the coefficients of the equations. I'll come back in a minute to this. But remember that one of the things that was discussed in the previous lecture was the construction of the moduli space for cubic curves. So basically that construction essentially was based on studying what happens and putting in normal forms, and something was attempted for Quarty curves. This approach in trying to understand things by equations is GIT. The second approach, I mean, there is Hoche theory. And this is based on varying or study of variation of cohomology. So in some sense, this is related to cohomology. And the third approach, this is what Eduardo is talking about, is the abstract point of view, where one starts with deformation theory, gets into stacks, and I don't know if there will be much discussed here. In the end, one gets into the theory of Kolar, Shepherd-Baron, Alexeyev. So each of these approaches, and maybe I will touch on this towards the end of the class, each has advantages and so on, and there are slight differences or big differences between them and things like that. So this is just to give you an idea what's going on. So here we are taking the approach that's kind of the most natural, that's probably kind of closest to, actually it's not quite true. I don't know if Riemann, maybe the classical Italian school in the late 1900s or something like this. So this is the geometric approach, the GIT, is simply based on studying the equations. So let me just say a few more words about this. So kind of why GIT. So we are given a class of objects. For simplicity, say genus G curves, say. And we want to construct a moduli space. This will be denoted kind of generically by M, sometimes by M bar. This would be the compact version. So what are the steps? The first step is what I will call uniform embedding. So we start with abstractly like a curved C of genus G, and we want equations, basically. Because this is, as I said, this is GIT. So what's going on? So if C is smooth, non-hyperelliptic, then probably everyone here knows that the canonical class defines a map, an embedding of C in PG minus 1. So it basically embeds the curve in a fixed projective space. In fact, we can allow hyperelliptic if C is any curve with a torus nodes, maybe connected or something, then the dualizing sheaf embeds C in a projective space, but this is kind of fixed. And here I'm taking a power, K power, and this depends on K, where K is larger than 3. So I'm starting with something quite abstractly, like a curve. I define like a smooth one-dimensional complex variety, and I'm saying that it has genus G. Remember, this is just the dimension of H1C omega C, OC. So I'm defining a curve this way, a genus G curve, and then it turns out that I can embed it uniformly in a fixed projective space. Which is good, because now, for instance, basically, for example, this is what was discussed. If I'm in genus 3, the non-hyperelliptic curves are the same thing as smooth plane quartics. Now, of course, if I want to cover all the curves and so on and so forth, I will have to go to a higher embedding. It will not be a hypersurface, and it will get more complicated. And I think this would be touched in Gabi's lecture. But in any case, so the point is that just at the conceptual level, I'm starting with something abstract, and then I'm getting equations for it. And this is kind of the key word here, is uniform. And similar results hold for varieties of general type, and for instance, for K-free surfaces. So for example, let me put here a theorem of Meyer. Says that if S, L is a polarized K-free, then the third power of the line bundle always defines a birational map to a fixed Pn, and this is birational, and this is with AD singularities. So this is actually as good as it gets. And similar results hold for say, varieties of general type. Why is that good? Because now is the step 2. Is for embedded objects, with fixed invariants. So if I'm embedding C into Pn, and this is kind of fixed invariants, there exists a parameter space which in general is called the Hilbert scheme. You have to specify the Hilbert polynomial, which encodes This encodes the invariants, the discrete, whatever the invariants, and the projective space. And this would be like a parameter space for all embedded objects. Okay, in general, this is kind of an awful object, but at least this we know that's like a projective algebraic variety. And of course, if we want, we can restrict to the smooth locus inside here. So you start with something very abstract, and you construct a parameter space for those objects. I mean, actually, you'll construct something much bigger, but kind of as an open subset in some component, there will be the smooth locus. And finally, the step 3 is you need to forget the embedding. So basically you need to mod out by change of coordinates, which in this case means that you need to mod out by the PGLN plus 1, and then in the end, your moduli space would be this U modulo PGLN plus 1, or maybe some sort of compact version would be the Hilbert scheme modulo this PGLN plus 1. Okay. So this gives you a basic construction. So you start with something abstract and you get to something that seems, so the point is that you get something, the moduli is a quotient of an algebraic variety by a group. That's kind of the mantra of GIT. Yeah.
Actually, things should be a little bit more complicated than this, because you want to take locally closed.
Yeah, I mean that's much more complicated, and I'm lying on many levels. But so as you said, I mean anyway. But the point, this was just a motivation to see how you get from something like curves to GIT, and we'll discuss. When we'll discuss the example of curves, we'll do so. You see there are many issues here and whatever, and but this just gives you an idea. And think about just to think concretely. Think about the genus-free curves. As I said, a genus-free curve, ignoring some of them, the hyperelliptic ones, they are the same thing as plane quartics. So the Hilbert scheme for plane quartics is what? This is, someone already said it in the previous lecture, is P to ND. Let's see if I remember. ND, so these are hypersurfaces, maybe 1 in Pn. So I think ND is N plus D, choose D. So let's see what is here. So this would be 4 plus 2, choose 4. Okay, maybe 15. No, it's P14, and then you mod out, let's see, by PGL3. So this is 6. Okay, so it looks right. Okay, so this gives you, I mean, of course, here you lose, and please pay attention to this example. So at least, I mean, one problem you see it kind of staring in your face, at least in this construction, you automatically lose the hyperelliptic curves because you don't see them as plane quartics. So you need to do something else and whatever. But this for instance, gives an idea why the moduli of genus-free curves would be a 6-dimensional algebraic variety. Okay, The problem is that GIT tells you, wait a minute, what you did here in the end will be okay, but you have to be a little careful. So basically, GIT is the study. So GIT is study of quotients in algebraic geometry. So the basic setup is that you have G in an algebraic group acting on X. So if you want, you can think G is PGL3 acting on X, which is P14, which is P of sim P of H0 or P2 or 4. So the question is, what is the quotient X mod G? So let's see, what do we want? We would like to have two things. We would like the points of the quotient to be in one-to-one correspondence with orbits of G on X. So this is the meaning of quotient. This is just kind of meaning of quotient. And the second thing that we want is to have some sort of surjective map such that both are algebraic varieties, and this map should be regular at a minimum, in particular continuous. So we want a quotient is the first requirement, and then we want this quotient to be somewhat in algebraic geometry. But these are contradictory, so these are kind of contradictory. And let's see why. The simplest possible example is the following. I'm taking X to be just C, or the affine line, and G to be C star. And I'm doing the action C star acts on C simply by multiplication. So T comma X goes to T times X. So here we note there are two orbits. So one is C star inside C, which is just the orbit of any point. So for instance, if I take C star times 1, and the other one is just 0, which is C star times 0. So the quotient C mod C star should be simply 2 points. But then the second requirement tells me that C goes to C star. This has to be continuous. So let's call these 2 points maybe O0 and O1. And let's call this map pi. So here I have, this is the set O0 and O1. Then if I'm taking pi inverse of O1, this is of course C star times 1, the orbit of 1. But this, by topological reason, this should be closed. But of course, C star inside C is not closed. So now maybe you can say maybe you have something more fancy, maybe the points are not closed or something, but even if you try to do that, it will not work. We'll see later what is kind of the correct answer in this situation. So basically, these two goals are contradictory. So you cannot have kind of one-to-one correspondence with orbits and at the same time to have also good algebraic properties. So let's put here two definitions. So definition. So, I mean, all today, G and X will always stand for an algebraic variety and a group acting on it. So basically, we can put the following two definitions. So we can say that whatever Q is a categorical quotient of X by G if it satisfies the following thing. So there exists a surjective, so there exists a pi from X to Q such that for any G invariant map F from X into Y, this means basically it means that F of G times X is F of X, so constant of on orbits. There exists a unique factorization. X goes to Q, and then I have Y, this is F, this is pi, and I want there exists, and there is this unique. So a quotient would be the usual thing, so this is X mod G. Maybe I'm using this notation. And what I want is if I have a map which is constant on orbits, then it factors through the quotient. This is somewhat kind of what I want there in specified in categorical terms. And let's note here something. What should we note here? We know that, suppose, I mean, the algebraic varieties are built out of affine varieties. So suppose that we are in the simple case where X is spec of R. And this R, I will denote just R of X. Let's remember, these are just the regular functions. So this is the same thing as function from X to the affine line, which are regular. So what will happen in this type of situation? So in this type of situation, let's see what's going on. If I have a, so assume that I have a categorical quotient. So I have a categorical quotient, and I want to understand the regular functions on this categorical quotient. This is kind of the question. So a regular function here is, of course, a map to A1. And then, of course, if I do the composition this way, I note that this is a regular function on X, which is invariant. And conversely, if I have a regular function which is G invariant, by the universal property, it will descend to a regular function there. So the regular functions here should be the regular functions on X, the G invariant ring. This is the ring of G invariant functions. And this is inside R. So I'm saying that if I have a categorical quotient and I want to understand what it actually means, kind of to go from categorical to something more concrete, I can look at the affine case, and it's kind of immediate to see that if a categorical quotient exists, it has to be the ring of invariant functions. On the other hand, kind of the thing I really want is a geometric quotient. And let's see. This is a definition. So given G acting on X, a geometric quotient of X by G is a morphism pi from X into Q such that I have the following properties. 1, pi is surjective and the fibers are exactly the G orbits. The second thing is that if I have some U inside Q open, this is equivalent to saying that pi inverse of U inside X is open. And finally, is that if U in Q is open, then the pullback gives me an isomorphism from the regular functions on U into the G invariant functions on the, so these are G invariant functions on the pi inverse U. So basically the first two are, this is quotient in the usual sense. And the third one is basically, this is quotient in the algebraic geometry sense. So the condition 3 is that if I have an open subset downstairs and I'm taking the regular function, this is an isomorphism, that's the condition, sorry. So I have always a pullback. So the pullback of downstairs regular function will give me a regular function here. And because whatever is clearly, this is G invariant, I have a map to the G invariant. So the condition is that I'm getting exactly the G invariant function. So there are two notions of quotient, and basically the upshot is that while categorical quotient exists, so yeah, so this is part of the data. So yeah, so this is a morphism. And of course, these are algebraic varieties and so on. Okay, so probably whatever theorem 0 of that, so theorem 0, which I mean, I guess I will call it Hilbert and Mumford. So let me put it in kind of, so categorical, good, and I will not define good, so good categorical quotient exists for affine varieties. So the good categorical quotient satisfies certain additional properties that basically will be included in the theorem. And let me not make another definition to confuse you more. But basically, a categorical quotient exists in large generality for affine variety. So let G be a reductive group. I'll come back in a minute to this one. And X, an affine variety. So this would be just spec of R. Then one. This is okay, I'll comment. The subalgebra R xg inside R, which is Rx, is finitely generated. So I'm considering, for instance, think about this as being the polynomial ring Cx1 up to xn. I'm acting, for instance, with SLN. Okay, I'm acting with PGLN or SLN, and that will be finitely generated. The second statement is that if I have F1 up to Fn generators of Rg, so any set of generators, then the image of the map defined by these things from X to An is closed and independent of Fi. So this image would be actually my quotient, and of course I'm getting a map from X into Xg. The third statement is that pi from X into X mod G, defined there, is a surjective morphism and satisfies the universal property. So this is being being a categorical quotient. And kind of the good part, let's see what is the good part. Kind of the good part, this is kind of the additional part. So let's see, this will be 4. If I have U in X mod G open, then the pullback from RU into R pi inverse U G is an isomorphism. If I have Z included in X closed and G invariant, G fixed, G invariant, then pi of Z is closed. And finally, if I have Z1, Z2 in X, closed, invariant, G invariant, and Z1 intersected Z2 is the empty set, then pi of Z1 intersect pi of Z2 is equal to empty. So So these are kind of the new kind of, you don't really get those from kind of being categorical quotient. It comes from the construction. So this is the good part, the existence of good quotient. And I'll comment on them. So basically, 1, 2, 3, this is basically the construction of quotient for affine varieties. This is kind of whatever, so this is kind of a good property for localization, if you want. And the last one is some sort of separation of orbits. I'll come back in a minute to this one. Let's see.
Can you understand why you restated the condition 4 that's the same of condition 3 before? The condition 3 of that was in
No. So 3. Wait a minute. So 3 is just that it satisfies this universal property from here.
No, it needs 3 from the definition of geometric function.
Oh, okay. 4, did I?
Can you understand that there is a reason or?
I mean, there is a reason that I didn't synchronize my labeling of the definitions or something, but okay. So of course you see that I have okay. So that's a good question in the sense that you see that 5 and 6 are weakening of the condition fibers is equivalent to orbits. So all the other conditions kind of hold on the nose. We just need to weaken a bit, and this was kind of the original example. We need to weaken a bit the condition that fibers are exactly the orbits. And this is what you can do. This is 5 and 6. So basically what I explained is that if you have a categorical quotient, then basically it has to be given by RG. So it has to be given by this one. Now it tells you that this construction, if you take the ring of invariant functions, this is the construction, gives you a categorical quotient, and in fact it also has this kind of good localization property. And then kind of moreover, and this is kind of why GIT is good, are these properties 5 and 6. And just, I'm running short on time, this is kind of, anyway, so just a quick comment. So for the first part, so kind of the first part is the algebraic statement that, again, I'm not very good with attributions, but I think more or less is Hilbert, that if G is reductive, R is a finitely generated K algebra. I mean, for me, K is C and whatever and stuff like that. So then RG is finitely generated. Okay, so a comment about reductive groups. Reductive groups. You should think of them of two types. First of all, there are the semi-simple groups, which goes into whatever classification, VGIT theory, root system, and so on. You should think here the things that we'll discuss here are PGL1 and SLN plus 1. But of course, here it includes SO, SU, exceptional, and so on, and tori. So this is, in this situation, you can think just powers of C star. So basically, a general reductive group will be an extension, a torus, G-reductive, and the semi-simple part. So the non-reductive groups, and I mean, I will not get into, I will not say anything more. You should think of kind of the opposite of reductive is unipotent, which you can think of being a subgroup of upper triangular Mie matrices. And that's a fact, maybe Nagata, counterexample to Hilbert, 14th problem, is that there exists RG not finitely generated if G is unipotent. And R is actually very simple, so R is something maybe C of x1, x2. I don't remember if you need free variables or something. So the Hilbert asking great generality if rings of invariants and more generally certain kinds of rings are finitely generated. I think he proved it for something like SLN, and then people generalize it easily to reductive groups. And then Nagata in the 60 or something, he gave a counterexample. And I think there are some nice examples of Mukai that are of geometric origin, and maybe you can understand them better. Anyway, so the point is that once you know the finite generation, you do this thing here, you get the quotient, and then you prove the additional properties. The additional properties 5 and 6 have to do so let's comment. So kind of separation of orbits. This is kind of 5 and 6 have to do with the behavior of orbits. So let's see some examples. So first of all, let's go back to C acting on C, T maps to T times X. Of course, here, the ring of function on C is just C of X. And if I'm taking the invariants, the ring of invariants is C of X. I'm acting by multiplication. It is obvious that the only things that are invariant, because I'm multiplying the variable by t, so the only polynomial that's invariant is clearly the constant. Another example, so the conclusion here is that x mod g in this situation is just spec of C, which is just a point. Exactly the same example, I can do it on C square. So here, I'm acting by t goes to t times x. So let me write it more carefully. So t acts on xy by going to t times x, t times y. Again, the ring of invariants is just C. I mean, I'm multiplying both variables by t. It is obvious that the only thing that remains invariant are the constants. So here the quotient, let me write it here, C square mod C star is just a point. Now you see that this is a bit of a surprise. Why is that a surprise? It's a surprise because, for instance, the dimensions are wrong. So maybe I can live with an example as the first one where I take C mod C star and I'm getting just a point, I'm collapsing some points. But this one is kind of, I have something two-dimensional, a group one, which is one-dimensional. This is just a point. Okay, let's try again. C2 t times xy goes to t times x, t inverse times y. What is the ring of invariance in this situation? So now I'm acting on polynomials. I multiply t by x and y by t inverse. So here there needs a small proof, but this would be just c of xy. So what will be the quotient in this situation? C square modulo C star in this situation is just spec of cxy. Abstractly, this is just spec of a new variable z. So this is just the affine line, or C in my notation. So you see, so something goes on, and I mean, so you wouldn't really, I mean, they look kind of the same, but kind of, you see the result is vastly different. So maybe we should take a look at the orbits. So let's look at the orbit behavior. So this is C2. This is C2. And now let's see. So in this situation, in both situations, I have 0, 0, which is a single orbit. So 0, 0. Maybe let's call example 2, example 3, just to keep it 2 and 3. Okay, so what's happening if I multiply t and y by x? Then all the orbits will look like this. So this is an orbit. This is C star times xy. So you see, so here the orbits are puncture lines, and here we see that the closure C star times any xy, if I'm taking the closure, this includes the orbit 0, 0, which is the orbit of the origin. On the other hand, in this picture, this looks differently. If I'm taking with x, y, and x different from 0, y different from 0, then you see the orbits will look like parabolas. This would be basically x times y is constant, because you see that I'm doing t times x, t inverse times y, and of course this would stay constant. So basically here I will get this type of orbits. There will be some special orbits. Okay, my picture is getting bad. So there will be, okay, hopefully you do it better on the So there are two special, so there are three special orbits. Special orbits. One is the orbit of 0, 0. Then is the orbit of C star times x0, C star times 0, y, and then all the others. You see that these two have the property they contain enclosure 0, 0. All the others turns out to be closed orbits. So let's make a general fact. So this is general fact. And here I don't think you need to assume basically anything. I don't think you need to assume G reductive. I don't know, maybe G acting on X. So I'll denote G dot X the orbit. So this is just the set of points G times X. And G, this is the stabilizer. This is the set G dot X equals G. Of course, the orbit lives in X. This equals X. This lives in G. Okay, so what is the statement? So first of all, the orbits G dot X are smooth, locally closed, subvarieties of X of expected dimension, of dimension equals dimension of G minus dimension of the stabilizer. And the second statement is that the closure of a given orbit, of an orbit, G dot X is a union of closed orbits of strictly smaller dimension. So in particular, as a corollary, you obtain that there exist closed orbits. And since I have only, I don't know, a couple of seconds left, so the upshot is that if I take X mod G, where this is affine and reductive, basically properties 5 and 6 imply that each point, the points of these quotients are in one-to-one correspondence with closed orbits. So let me just read what I said the last thing. So if I'm taking the affine quotient of X by a reductive group, then initially my hope was that the quotient will be in one-to-one correspondence with the orbits. This is not true by trivial examples, but it turns out that something weaker is true. There is a one-to-one correspondence with closed orbits. And let's just see here, in this example, remember the quotient is just a point, which means that 0, 0 is the only closed orbit. Here instead, the quotient is C. And of course, in C, I will have 0, which corresponds to 0, and everything else C star. Let's call it A. So let's see if you followed. So if I'm taking a point, so I'm saying the theorem tells me that the points of X mod G are in one-to-one correspondence with closed orbits. In this particular example, in the example 3, I did a computation of the ring of invariants, and I got the conclusion that the ring of invariants is just C. It's just one-dimensional affine line. And now I'm trying to establish the correspondence between the points of the quotient, so the points of C, and the orbits upstairs. So what is this correspondence? So I already kind of gave you that 0 corresponds to the closed orbit 0, 0. What about another point, non-zero, A there? So what is the orbit upstairs corresponding to it? So A from there would, of course, correspond to something like x dot y equals A. And that's kind of like the parabola will go to that, and this is a closed orbit. Is the orbit, of course, kind of here, why are the orbits smooth? Is because they are homogeneous varieties. And from there, kind of, for instance, anyway, I'm already over time, so let me stop here.
I don't understand the second condition. Is the closure the union of the closed orbits?
Yeah. Okay. Okay, you are right. So, okay, yeah. Is a union of smaller orbits, and in particular, there exists closed orbits, and basically this is kind of, it will be exactly one in each orbit closure. So you see that if I have, I mean, I will have smaller things, and they are kind of nested. The smallest one, the minimal dimension, has to be closed. And actually, there is something to argue, which is part of the statement 6, that I cannot have two closed orbits in the same fiber. But that's kind of whatever, if you unwind what I said there.